Okay, back to the problem. So let's take a look at how to go about this guy. The admittance I can write down immediately. Inverse ohms, and I won't write down the units. I'll just assume everybody knows it's inverse ohms, and then plus 1 over 4j. Well, this equals 0.5 minus 0.25 j. Okay, and got a little problem with the pen marking correctly. There we go. Oops, erase these two. Rewrite it so you guys can see it easier. Reciprocal of j, the imaginary constant, the reciprocal of j is going to be negative j, by the way. That's just something to put in the back of your mind. Remember when you're working these problems. Okay, now we want to find what the current, the equivalent, so we've got the equivalent parallel impedance. The voltage is going to equal, excuse me, take that, let's back that up just a second. We want to find the current. The current we've got is going to equal voltage times admittance. Current times impedance is voltage, which makes, and the impedance is the reciprocal, the admittance. So you could write this as V over Z of the two parallel components. You could write it like that. Okay, we have the admittance here. We have, it's easier this way. The only thing we need to do is convert either the voltage into complex notation or the admittance into a phasor notation. So let's go ahead and do that. Let's convert the admittance to phasor notation. So the current is going to equal 60 at the angle 45 degrees, units of volts, times. Let's figure out, crunch the numbers and figure out the magnitude and phase angle of the admittance. Okay, ladies and gentlemen, I'm back. I opened up New Octave, which it's a program that works just like MATLAB. It's got a different user interface, but the command line is just like MATLAB. So the first thing I do is enter what the admittance is, and 0.5 minus 0.25j. I got to get over to the window, I just realized. Okay, there it is. Now, I want the phase angle and the I want the phase angle and the magnitude of YP. So I'm going to go YM for Y magnitude equals absolute value of, use the same absolute value, decimal absolute value as, DC, or real number absolute value, and imaginary number absolute value are the same thing, 0.559. And then the phase angle, YA, I'll call it Y angle. The angle, the phase angle of the variable Y. So we're going to make that the argument of YP. So this tells me the phase angle in radians. So to convert to degrees, there's 180 degrees per pi radians. There we go. So this gives me the phase angle. And now it's just pretty simple addition. The current is equal to 60 angle 45. Let's go back to here. There we go, octave. So this would be 0.55902 angle 26.65. I'll round it to three significant digits. And negative 26.565. Negative 26.565. And now we multiply this times this. So that would be YM times 60, 33.351. The angle would just be 45 minus the 26.565, or plus the negative 26.565. So it's 45 plus the variable, the argument variable. There we go. 18.435. Okay, that ought to do it. We have the current, and we have YP, which we can write 0.559 angle negative 26.565. So we've got YP and we've got the current. So let's see what the book says. So same thing. They say the same thing as I did. ZP, they calculated Z, and which I don't think is necessary. Okay. They are showing you though that the reciprocal of Z is Y. This complex number here. So I skipped writing the complex number. I went directly from this to the phasor notation. And now they go to the phasor notation. Same answer as I got. And finally the final answer. Yep, same as I got. Okay, your turn. So I've gone through an example. Now it's your turn to do an example. And I'm going to go ahead and end the video here and pick it, and I'll go through the book example on the next video. So pause, do the example, and come on back. Try these things. Don't just go, oh, skip it over. Oh, I know how to do that. You need to practice a little bit. Everybody needs practice. Ending the video here, on to the next video.